let's do an example problem. So let's do an example problem that's centered around viscometers. Viscometers. So a viscometer is a tool that is used to measure viscosity. And there are many such tools, but one particular type of tool is that of a disc. So imagine I had a disc like this, and I squirted some viscous fluid between this disc, which can rotate, and a stationary plate underneath it. And then I also had a stationary plate on top, but obviously we want to be able to see what I'm doing, so I'm not showing that. Then I take this disc and I rotate it at some particular rate, with a shaft or something like that sticking in the top, and I measure how much torque it takes, how much moment I need to apply in order to keep this disc running at rotating at a constant velocity. And it turns out that this is a lot more convenient than using parallel plates, right? Because parallel plates, as soon as I start moving this plate, I'm going to run out of space, right? I don't have some infinitely long hallway that I can keep moving this plate, trucking it along. And oftentimes it's a lot easier to measure moments and to measure rotation rates than it is to measure forces and linear velocities. So we use these plate-based viscometers to measure the viscosity of fluids. And if we think about it, if I squirted some fluid in between this plate and the ground underneath, as this plate rotates, there's going to be a velocity gradient between the moving part of the plate and the stationary part of the ground underneath it. So as long as we're careful in how we analyze the fluid mechanics going on in between the plate and the stationary ground underneath it and the stationary wall on top of it, as long as we're careful about how we analyze that fluid mechanics, we can infer what the viscosity of the fluid is from a relationship between how much moment I need to apply to keep that thing rotating and what its rotation rate is. So let's sort of map out what our problem-solving strategy is going to be for this example problem. So we have our disk, and it's rotating at some particular rate, and there's also some particular torque that we need to apply in order to keep the disk rotating at that speed. And then some other factors are going to play a role, for example, like the radius of the disk and the thickness of the gap between the disk and the ground underneath it, and the disk and the stationary plate on top of it, right? So we're sort of working out, we'll need to work out all of those things. So, and of course we're going to draw upon some concepts that we've talked about in earlier lectures, for example, like viscosity and shear stress and the linear velocity profile, etc. All of those sorts of things. So let's sort of map out what our problem-solving strategy is going to be, how these pieces of information and how these parameters relate to one another. So ultimately what we're looking for is a relationship between the rotation rate of the disk, right? This is going to be something that has units of radians per second. And all the way on the other end of what we're trying to relate it to is the torque, or you might call it a moment, the torque or moment that we need to apply is the torque or the moment required to sustain this constant rotation rate. And of course, this is going to have units of Newton meters as torque is. So we're essentially looking to map, to use fluid mechanics and sort of other reasoning to get some kind of relationship between these. But we can't necessarily jump, straight from this to this. How is this going to how's this all going to work out? So we have some rotation rate of the disk. We're going to be able to relate the rotation rate of the disk to essentially point velocities, to velocities of points on the disk, right? So if the disk is rotating at some speed, we're going to be able to estimate the velocities of various points on this disk. And if you recall, velocities close to the center of the disk move slowly, points on the edge of the disk move faster, right? So we have this idea, and all of these velocities are going to scale with the rotation rate of the disk, right? So we're going to need some relationship between the rotation rate of the disk and velocities of points on the disk. And in particular, I'm talking about sort of what the linear velocity of those points on the disk. So that's going to be meters per second. So we're gonna want to work out a relationship between these two. Well, if we can gain some information about velocities of points on the disk, if we sort of look at things from the side, the velocities of the points on the disk and the stationary floor, the stationary wall underneath the rotating disk, there's going to be a velocity gradient between those. So if we have velocity of points on the disk, and we kind of use a shortcut of the linear velocity profile that we talked about in the previous lecture, we're going to be able to work out a relationship between velocities of points on the disk and velocity gradients in the fluid in the gap between the moving disk and the stationary floor or ceiling underneath it or above it. Right? So, and of course, velocity gradient, right? This is going to have units of meters per second per meter, or 1/seconds. So the velocity gradient in the fluid in the gap is going to help work us out. Now, if we have velocity gradients, and we're dealing with, let's say, a Newtonian fluid between the disk and the walls, then we can work out a relationship between a velocity gradient in the fluid and shear stress that arises from that velocity gradient. So we're going to work out a relationship between velocity gradient and shear stress on the disk, right? And of course, shear stress is going to have units of newtons per square meter. If we have shear stress acting on that disk, then that shear stress is going to essentially apply a bunch of little bits of force, right? If you imagine, this disk is spinning, shear stress is acting kind of throughout this disk. The shear stress is going to apply a bunch of little bits of force. A bunch of little bits of force that are going to sort of oppose the motion of this disk, right? So if all this shear stress is going to act on little bits of area of this disk, and it's going to result in little bits of force being applied to this disk, right? So shear stress is going to result in little bits of force on the disk. So shear stress is going to result in bits of force. Which of course has units of newtons. And these little bits of force, you can imagine if all these little bits of force are acting with some lever arm, some moment arm from the center, right? If I have some little bit of force that's opposing the motion, acting some distance from the center of rotation of that disk, that force essentially applies a moment about that center. And it's those moments that are applied moment is going to need to perfectly balance in order to sustain this thing at a constant rotation rate. So little bits of force, we're going to end up with a bunch of bits of moment or torque. Okay, so all these little bits of force are going to result in all of these little bits of moment acting on kind of all of the little bits of area on this disk. So all these little bits of force are going to result in all of these little bits of moment or torque. And then if we add up, spoiler alert, integrate all of these little moments, then there's going to be some overall moment from all of these little bits of torque that our applied moment is going to need to perfectly counteract in order to sustain a constant rotation rate, i.e. no angular acceleration. Right, so we're going to have this problem-solving strategy that all of these kind of balance each other out. All right, so let's work out. Let's try to work out this relationship between all of these concepts, so we can get the torque required to sustain the constant rotation rate as a function of the rotation rate of the disk and various other problem parameters that are going to be important. For example, the gap thickness, the radius of the disk, the viscosity of the fluid, etc. So let's work it all out. So I'll just sort of sketch what the system looks like. So we have some disk. Some disk like this, and the ground is under the disk, and there's some thickness essentially between the disk and the ground, and there's also a plate on top of this disk that I'm not going to draw. The disk has some handle that kind of sticks through, and the disk rotates. This disk rotates at some rotation rate, capital omega. Right, so we're rotating the disk at some speed, capital omega, and we want to know what torque we need to apply to this disk in order to sustain the disk's rotation at capital omega. Some problem parameters that we do know is the radius of the disk, right? I could take out a pair of calipers and I could measure the radius, or maybe the diameter, but infer the radius of the disk. I might say that there's some gap between the bottom of the disk and the ground underneath it, and also some gap thickness between the top of the disk and the ceiling above the disk that I haven't drawn here. So the gap thicknesses, I'm going to call little h, and we can treat that as a known parameter. And let's just say, although in practice this device would be used to measure and characterize the viscosity of the fluid, let's pretend we knew the viscosity of the fluid and we wanted to guess what the torque was, right? So the fluid viscosity, right, so the fluid viscosity is what I'm going to call mu, and this is the rotation rate of the disk. All right, so we know some information about the gap thicknesses between the moving disk and the stationary walls. We know the rotation rate. We know the fluid viscosity, and we want to infer what the torque is, to sort of predict how strong of a motor we need or something like that. All right, so oftentimes when we're setting up problems like this, it's useful to define some kind of coordinate system. So I'm going to define a coordinate system where little r is a coordinate that we're going to sort of analyze lots of points on this disk. We're going to analyze lots of points on this disk. So little r is going to be the coordinate of some point between the center and the outside edge of the disk, whereas capital R that I'm putting in blue is going to be like the physical radius of the whole disk, right? So r is going to be sort of the position of some point on the disk that I'm analyzing. Capital R is the radius of the whole disk. All right, so these are the problem parameters. So let's sort of look at what a side view between the disk and the stationary ground under. So I tried to draw a sort of 3D view here, but now let's do a side view. So let's say I have the disk like this, the ground underneath it, and of course there's a ceiling on top of it, and you can imagine the sides are enclosed, but we're not going to analyze too much with what's going on the side. There's a handle that comes out of the disk like this, and you can imagine so the thickness, the gap thickness here is h, And we can imagine that points on the disk, if the disk is rotating about this vertical axis, points on the disk are kind of moving with some speed, right? There's some speed that, that this point on the disk is moving with, but points on the ground underneath it aren't moving. So what does that mean? That means we get a linear velocity profile, or that means we get at least some velocity profile and hence some velocity gradient between the stationary points on the boundaries and the moving points on the disk, right? So we essentially have velocities here. And if we think about what's going on with points on the top, points on the top are kind of doing the same thing, just sort of in reverse, right? So the points in the disk are moving fast, and then all the way up at the ceiling, the points aren't moving at all. So we sort of have these two velocity profiles with their respective velocity gradients between the stationary walls and the moving disk. And this is what gives rise to that shear stress. So in practice, these don't necessarily have to be linear velocity profiles, but for simplicity's sake, and in a lot of times, as long as these gaps are pretty narrow and you're not moving the disk too fast, you do indeed get a linear velocity profile between these. So we're just going to go ahead and assume that we have a linear profile between the moving disk and the stationary wall. So we're just going to assume that we have a linear velocity profile. And the rigor that we would need to go to prove that is a little beyond what we want to cover right now. But here I've sort of drawn what some single velocity profile looks like from the side view, but there's not going to be some single velocity profile that really applies to all of these points on this disk. So if we have this disk here and it's rotating, we know that points at the center move pretty slowly compared to points at the edge, right? And in fact, the point at the very middle doesn't have any velocity at all, right? So what does that mean? That means that points close to the edge of the disk are going to be moving faster, but since the gap thickness is the same, the points at the edge are going to have a much more intense velocity gradient than the points close to the center of the disk, right? So, close to the edge, where the velocity of the disk is a lot faster, I'm going to have a lot more of a delta velocity for that over that same height thickness. So, what's going on here? Basically points at the edge of the disk are going to be moving very fast, whereas that speed of the points on the disk is going to be decreasing as we move closer to the center of the disk, right? So we have a velocity profile in this direction here, but we also have a different velocity profile essentially with every point on the disk as we go from the inside to the outside. So, yikes, we're gonna need to sort this out. So let's in addition to we expect the velocity of the disk essentially to be a function of little r, right? A function of our radial coordinate on the disk. So let's just sort of make two coordinates, one r and one y. So y is essentially like the distance between the very bottom and the point on the disk, right? So y is this coordinate, r is going to be this coordinate. So for simplicity's sake, what I'm going to do is I'm just going to analyze what's going to happen in the sort of bottom half of the disk, and we can then just whatever result we get from the bottom half of the disk, we can just double that torque, because we're essentially neglecting the details of what's exactly happening with this right in this region here. If we sort of neglect what's happening right there, any shear stress, any forces, any moments that we get from the bottom of the disk would just be doubled since there's the symmetry at the top. So we're just going to analyze what's going on in the bottom, and then we're just going to double our result to get to what's going on the top. So we're analyze So we're going to analyze the bottom face of the disk and then just double the results to get what's happening with the full disk. So let's so if we're going to work out what the details of this velocity gradient is, we're going to essentially need to know what the velocity of various of points on the disk are, and we're going to need to essentially get what this velocity of the points on the disk is as a function of r. So let's kind of work out an expression for that. Let's basically say we want an expression for velocity of points on the disk as a function of our radial position r. And if you so take a moment now, maybe perhaps dust off your dynamics or biomechanics notes, pause and ponder. What is the velocity of points on the disk as a function of radius and other known parameters that we've given in the problem? So pause, ponder, and consider. All right. So if you remember, for rotating things where the center isn't moving, the linear velocity of a point on the disk is just the radius from the center times the angular rotation rate of the thing, right? So it's like, remember the omega r business? Well, we know omega, right? We're treating the rotation rate of the disk as unknown, and so each point on the disk has its radius r, and if the angular rotation rate of the disk is omega, the linear velocity of those points on the disk is going to be omega r. So the velocity of some point on the disk is going to be omega times little r, right? And we want this, we essentially want a function kind of that could apply to any point along the disk, not necessarily just the points on the edge, right? So that's why we're doing little r instead of capital R. All right, so with this sort of analysis here, with the velocity of the disk, with some points on the disk being capital omega, which is the constant rotation rate of the disk, times r, the position that we are on the disk, I would say we've successfully squared away velocity of points on the disk in terms of this rotation rate on the disk, right? So we've kind of squared away these things here. We have this relationship formulated. So now let's try to look at, hey, do these velocities of the points on the disk, do they inform the velocity gradient in the fluid and the gap, right? So we already have this idea that there's a velocity gradient of the fluid and the gap, but can we get them in terms of this velocity of the disk? Well, for a linear, if we think back to the problem that we solved in the previous lecture, right, where we had some flat plate moving at some speed v plate in some distance here, we basically said, hey, we analyzed this pretty rigorously, and we said that there's some velocity gradient in the disk, dvx dy, and we ended up finding that it was sort of equal to, for a linear velocity profile, the velocity gradient is essentially the difference in these two velocities divided by the thickness between them, right? So the velocity gradient dvx dy for a linear for a linear velocity profile, dvx dy is essentially the difference in the velocities between let's say the moving thing and the stationary thing, the difference in velocities divided by the thickness, let's say, h, right? So the velocity gradient is simply just the difference in velocity divided by the thickness. Wait a second. Does that mean, do we need to go through such a detailed velocity gradient analysis as we did last time with the plate? No, actually we don't. We just need to look at, hey, what's the velocity of the point, of some point on the disk? What's the velocity of the ground? Well, the velocity of the ground is 0. So in this case, the delta v, our velocity gradient, we can kind of take a little bit of a shortcut here. With the assumption of the linear velocity profile, our velocity gradient is simply just going to be v disk divided by the gap thickness. And in this case, the gap thickness is this constant, little h, that was sort of given, an assumed known or an assumed given for the problem parameter. Ooh, that's nice. So what does this mean? Well, this means we have our velocity gradient in terms of some expression that we've already developed and a known constant for the problem. So, awesome possum. What do we got here? We now have a relationship between velocities of points on the disk and the velocity gradient for the fluid in the gap. And notice that this velocity gradient in the fluid gap, right, so we can take it, we can sub in the velocity of the disk right here, right? We can sub in this expression here, and that's simply going to be capital omega in the numerator times r divided by the thickness h. So what does this mean? This means that the velocity gradient is dependent on where you are in the disk, right? So what does this mean? This means we have a more intense or a steeper or a stronger velocity gradient at the edge of the disk compared to the center, right? Or that we have a variable velocity gradient over the edge. And if we have a variable velocity gradient at the across the disk, this means that we have variable shear stress across the disk and variable forces from that shear stress and variable moments from those forces. Oof, what a mess. Are we going to even be able to solve this? Yes. Persevere. Persevere. We'll do it. We'll do this together. All right, so what are we going to do here? So we're now going to try to say, hey, now that we have information about this velocity gradient of the fluid in the gap, let's try to work out this the relationship between velocity gradient and shear stress on the disk. So if we have a velocity gradient here, right, this is the velocity gradient that we got. In terms of knowns, constants, etc. Now that we have a velocity gradient, we need to use this velocity gradient to try to figure out what the shear stress is on the disk. So, in general, or I guess not in general, but I think in the problem statement, you know, I said there was some fluid viscosity here, and by using mu, I sort of implied that it was Newtonian, right? So if we're assuming Newtonian, then we can use a velocity gradient shear stress relationship. So what does this mean? The relationship between shear stress and velocity gradient for Newtonian fluids is tau yx is equal to minus mu times the shear stress rate or the velocity gradient. So in this case, dy. And actually, I was a little bit sloppy here. I said dvx dy, but of course x doesn't really exactly make sense here. We're actually really talking about sort of velocities in the theta direction here, right? So this is really like a dv theta dy. Anyway, the details aren't super important. Just a little bit of clarification in terms of what the subscript is. So that should really be dv theta dy. I digress. Anyway, but what does this mean? We have an expression for this that we can plug in, right? So for Newtonian fluid, this relationship applies, and we can now we have the expression for velocity gradient that we can now sub in here. So what's this going to look like? We now have minus mu omega over h times r. So as expected, we have a stronger velocity gradient at the edge of the disk. So now what does this mean? This means shear stress varies over our disk. So, what implications does that have? Well, let's take a look. At least now we've squared away what shear stress on the disk is going to look like. But we're going to need to analyze this a little bit more carefully, a little bit more rigorously, a little bit more calculus-y than we did when we were doing the problem last time of just the flat plate, of going between stresses and forces. The tricky thing being this time is now we have a variable shear stress, a variable amount of shear stress over the surface of the disk. So that's going to introduce a little bit of trickiness. So how do we deal with this varying shear stress, right? In terms of how that shear stress results in force and how those forces result in moments. How do we deal with a variable shear stress profile? Right? So if we have this variable shear stress profile, how does that impact our analysis? Well, ultimately what we're shooting for is the overall moment required to sustain this constant rotation rate. So if I think about my disk here, I'm just going to kind of draw a top view of that disk. And if my disk is kind of rotating with this rotation rate, capital omega, about my point here, we have shear stress that's acting on this disk. And in general, when we talk about shear stress, the way to relate shear stress to forces is that force sort of in general is equal to a stress times an area. But the tricky thing with this problem is our stress is variable, right? So we can't just take some stress. Stress isn't some singular quantity that we can multiply by pi r squared to get some force or something like that, right? So we don't really have, we can't just multiply stress by area and call it a day. We need to analyze things in a little bit more of a sophisticated way, right? So what I could imagine is I could imagine a little chunk of this disk, maybe here, right? I could imagine another little chunk. I could imagine another little chunk, right? I could break up this disk into a bunch of little chunks, and notice that if the motion of the disk is kind of going this way, that the shear stress is kind of acting on all of these little points, right? So I could basically say, hey, shear stress is acting on all of these little areas, and if I make these areas infinitesimally small, then I can kind of square things away, right? So this idea of force equals stress times area, we're not going to be able to do, not for our whole disk. Right, we're not going to be able to apply this type of analysis for our whole disk at once. So instead, what we're going to do is we're going to basically say that there are a bunch of little infinitesimally small forces, dF, right? That each little chunk of this disk has some tiny little dF acting on it. And in that case, then all the little dFs are going to be tau yx times the little infinitesimally small areas that belong to each of these chunks. Right, so instead of dealing with some singular, some total force times some constant stress times the total area, we're going to break up this disk into a bunch of little chunks. Each little chunk has some small force dF on it and is acting only on its small area dA. And then we're going to use calculus to essentially add up all of those little forces, because integration and calculus is essentially just summing up all of those infinitesimally small bits. So this is going to be our approach here. We're going to work out this infinitesimally small force. So we know these infinitesimally small forces can be stress times area, and over the scale of each of these little chunks, then we can then we can sort of work it all out. So we have these little df's, and we can plug in our expression. We can plug in the expression we got earlier for shear stress into that right here. So an infinitesimally small force somewhere on the disk is basically going to be this expression here. So some infinitesimally small force is equal to shear stress times the area that shear stress is acting on. So what does that mean? We now have developed a relationship between shear stress and bits of force that arise from that shear stress on the disk. But we don't care that much about force, right? In terms of this rotating disk, there's actually no net force, right? Because like there are forces this way on the top and forces this way on the bottom. Forces this way and forces this way. There's no actual net force on the disk. We're interested in the moments. So we need to consider the fact that all of these little bits of force are acting with moments, and those moments are going to resist the motion of the disk. So we've squared away what an expression for these bits of force is going to be here. But how do these force relates to moment? How do these bits of force result in moments? And we haven't totally squared away this idea of like, what is the most sensible, what is the most sensible way to break up this disk into tiny bits of area? How can I, how do I sort of mathematically define what the, what the areas of these little chunks are? What's a logical way to break up the disk into a bunch of little chunks? So two questions that we haven't really answered. How do I break up the disk into a bunch of little chunks, right? What can I algebraically put in for little bits of area? And how do these forces relate to moments? So let's try to answer those questions now. So if I take my disk and I notice, if I take my disk and I think about donuts. Actually, I try not to think about donuts too much because I'm super hungry right now. But if we think about donuts in a mathematical way, I could take this disk and I could break it up into a bunch of rings. Maybe in Calculus 1, you might have done like, integrating to figure out the areas of a circle, right? You might have sort of broken up. You might have done like shells or something like that. We can sort of break up this disk not into sort of like weird little segments like this, but let's actually make our segments rings like this. So we're going to break up our disk into concentric rings. And this idea of breaking up a whole thing into a bunch of concentric rings isn't going to apply just for this problem. This is going to be a strategy that we use over and over in the context of this class. So buckle up, we're doing it. So we're going to take our disk, we're going to break it up into a bunch of concentric rings, and we're going to make each ring have a thickness, an infinitesimally thin thickness, dr, and we're going to sort of assume that each disk is at a radius r from the center. So how does dA relate to each of these things? Well, dA is essentially what we get if we take this little infinitesimal ring right here, and we unwrap it, right? So if we take this ring and you could imagine unwrapping it into a little rectangle, that's the same, that sort of has the same dimensions as this original thing, what would be the area of this rectangle? So take a moment, pause and ponder. Pause and ponder, what is dA? What is the area of this infinitesimally thin shell that we've unwrapped? So take a moment, pause and ponder. What is dA in terms of in terms of some of these parameters. All right, so hopefully you've paused and pondered successfully. So what is dA? Well, dA, we can imagine if we take this ring and unwrap it into a rectangle, it's essentially a rectangle with one dimension dr and another dimension that is the circumference of this. And if we make them infinitesimally thin, then we don't need to worry that, strictly speaking, this isn't a rectangle if we unwrapped it. We make it infinitesimally thin, then essentially it's just a rectangle where one of the dimensions is this inner circumference of this right here. So it'd be like 2 pi r. So in this case, dA is 2 pi r dr. So there we have it, right? So now, why did I want to break this up? Why did I want to break up this disk, instead of into little patches, little dA patches like this? Why did I want to break it up into this concentric ring? Well, if you imagine the shear stress at any point on a ring like this, all of the points on this ring are the same radius from the center. So shear stress is actually constant for all points on one of these rings that have formed this way. So shear stress is constant for all on this ring. Of course, different rings have different shear stress, but shear stress is constant for all points on this ring. So what does this mean? We can kind of imagine each little bit of shear stress is holding back on the ring in exactly the same way. So shear stress is constant for all points on this ring, and so shear stress is constant for all points on this ring, and each point on this ring, so each point has the same moment arm about the center. So how is this helpful to us? Well, if shear stress is constant along all points in the ring and each point has the same moment arm about the center, we can kind of say, hey, all of the contributions from all of this stuff, from all of this little chunk, are sort of constant for any given ring. And then all we need to do is add up the contributions from all of these rings to the overall moment. Right? So what does this mean? If I think about moments, in general, a moment is equal to some force times the moment arm. And each point on the disk has a different moment arm from the center as all the other points, but all these points along these concentric rings have the same moment arm as each other. So what can I do? I can break up the, I can kind of consider each ring has some contribution to the overall moment. dm is basically all of the moments associated with the little forces on each ring. So dm is force times moment arm. Well, the force on each moment arm is what I call df, right? I'm assuming, I'm breaking this thing up into little chunks. Instead of little chunks that look like this, I break it up into a little chunk like this. So df times the moment arm for each of these little bits of force is r, right? So dm times this. Now I can sub in my expression for df that I had over here in terms of things that I care about in known quantities. So what can I do? I can sub in this expression for df. Right? I'm just going to move the r out front, this r out front, and then put in df here. Times dA. But wait a second. We also now we have an expression for dA as well that we can sub in. So what does this mean? This means my dm is minus mu omega over h. I have one r here, one r here. So this is r squared. And then when I sub in for dA, I get a 2 pi r dr. So times 2 pi r dr. So this expression here is the moment arm. This right here is the moment arm from one ring. One ring. So the moment arm from one ring is this little chunk right here. So let's see where this takes us. So where does that get us? We now have an expression for each little bit of moment from each of these rings, right? So we have a whole bunch of rings. Each of these rings has some contribution to the overall moment from all of the shear stress on this thing. So we now have an expression for what each little bit of moment is, and if we essentially added up what all of the moments from all of those little rings are, if we add up what the moments for each of those rings are, then we're going to get the overall moment from all of that shear stress, and that will inform what the overall torque is in order to counteract that shear stress to keep us in steady state rotation. So let's work that out. So in general, if we want the overall moment, from shear stress on the bottom, on the bottom face of this disk, let's say M for the bottom, then that's going to just essentially equal to the integral of all of the little dm's. Right, so if we integrate all of the dm's from all of these concentric rings, if we add them all up, i.e. integrate them, then we'll get the overall moment from all of those little dm's. So all we need to do now is just plug in our expression for dm into here and think about what limits of integration are sensible. So the moment on the bottom is going to be an integral of, and we can simplify some of this stuff as we put it in. So it's going to be minus mu omega over h. And then if we think we have an r squared and an r right here, we're going to get, well, 2 pi is actually sort of a constant, right? So we get 2 pi. And now the r squared and the r, we get an r cubed. And we have a dr. So let's think about what limits of integration we do. Well, essentially, we're adding up rings that started at the very center, and the rings went all the way to the outside. And of course, once we're outside the disk, we don't have any more. So we're essentially starting with the rings associated with the radius right at 0, and those rings go all the way to the outside of the disk. So the corresponding limits of integration, we're integrating with respect to r, right? The limits of integration are going to be from 0 to capital R, right? Where capital R is the radius of the whole disk, right? So little r is the radius of any one particular ring, whereas capital R is the radius of the whole disk. So capital R is going to be the upper limit of integration when we integrate with respect to little r. So take a moment now, pause and ponder what we get from integrating. So go ahead, dust off the high school calculus, see what you get from integration. So when we integrate, we can take a bunch of stuff out, right? If we consider, if we're integrating with respect to r, all of this stuff is going to be constants that we can pull out of the integral. So in this case, the moment associated with shear stress on the bottom of the disk is going to be equal to, minus mu omega over h 2 pi. And then if we integrate r cubed, remember integration, when you integrate you increase the exponent by 1 and then do 1 over whatever that new exponent is. So we now have 1/4 little r to the 4th, and of course we want to evaluate this from the lower limit of integration to the upper limit of integration, 0 to capital R. When we do that, we end up with minus mu omega over h 2 pi 1/4 capital R to the 4th, and of course the lower limit of integration we just have minus 0, so I just got rid of that. Okay, so here we are. We can of course simplify this just a little bit more, canceling out this 2 and the 1/4. So now we have minus mu omega over h pi over 2 r to the 4th. And then if we wanted to consider, oops, sorry, that was a little cut off on the screen. If we want to consider what the overall torque needed, the overall torque applied is going to essentially, we're going to need to double this. So the overall torque applied is going to need to be 2 times whatever we had here. So that essentially just gets rid of the 2 in the denominator. R to the 4th. So the overall torque applied in order to sustain this motion is going to be this. Now granted, like I was a little sloppy about minus signs. So you know, basically whatever direction we're rotating in, the torque that we're going to need to apply, I guess, should be in the same direction as that, right? So actually, I guess, right, the moment from the shear stress is acting in one way, so the torque applied should be the negative of the negative times 2 times whatever we got here. So the torque applied is essentially positive this. So let's look at this result. So anytime we get some result, we should do a couple of sanity checks, a couple of analyses to make sure we got the first result. So what are some sensible things to do? Well, consider, maybe even pause to consider, what are some sensible sanity checks to make sure we got a sensible answer right here. So could pause and ponder if you care to. I think 2 sanity checks that I like to do. Number 1 is, remember, baby you know who? Baby you know who really cares a lot about units, as do I. So if we care a lot about units, we want to make sure that whatever units are associated with this term here should have the same units as torque, or have the same units as moments. So let's analyze that. So first, let's analyze units. Unit check. Unit check, unit check. So what should we do? Viscosity, if you dust off your notes, is going to have units of kilograms per meter second. A rotation rate, strictly speaking, has radians per second, but if you remember, radians secretly aren't units at all, right? Radians are essentially unitless. So the numerator right here is actually really just inverse seconds, right? So radians per second is actually really just like 1 over seconds. H in the denominator here, we have meters. And then r to the 4th is going to be meters to the 4th. So what does that mean? So if we analyze things, you know, meters to the 4th cancels with 2 of these meters down here. So we have meters squared. We have 1 over seconds in the numerator, so that's seconds in the denominator. And then we have kilograms. So we have kilograms meters, sorry, got cut off a little bit. We have kilograms meters squared per second, or kilogram meter per second. We have 1 over seconds here in the numerator, seconds in the denominator, so this should be seconds squared. Good catch. So kilogram meter squared per second squared is the same as kilogram meter per second squared meter, which is the same as a Newton meter. All right, so what does this mean? We have Newton meters here. Is this units of torque? Check, we got it. All right, so unit check successful. All right, so after a successful unit check, I also like to just sort of do some reasoning about ups and downs. If something goes up, if something goes down, how does that impact the final result? So, what happens if I increase viscosity? If I increase viscosity, then that increases the torque applied, right? If I increase this, that increases. That makes sense, right? It's going to be a lot harder. It's going to be a lot harder to rotate a disk if I squirted a bunch of honey in there compared to if I just left air in there, right? So increasing viscosity increases this. If I increase the rotation rate, then that also increases the torque applied. And that makes sense too, right? If I try to spin this thing faster, it's going to require a lot more torque in order to counteract all of that shear stress, all of that velocity gradient business that I got, right? The velocities and the velocity gradients scale with the rotation rate, so the torque should scale as well. If I increase the gap thickness, then that decreases the torque that I applied, right? And if we think about it, if I had a much narrower gap between the rotating disk and the walls, then the velocity gradient would be higher, right? I would have a lot more change in velocity over a shorter distance. So having h in the denominator here, if I increase that gap thickness, then I lessen my velocity gradients, lessen all the shear stresses associated with that, and lessen the torque that arises from that shear stress. So increasing h decreases this, and that makes sense. And then the final thing is if I increase the radius, then that increases the torque applied. And actually increases it quite a lot. So not only, if I increase the radius, not only do I increase all the area that shear stress is acting on, but I also increase the moment arm that each of those little bits of shear stress are acting on. So that's why there's such a strong dependence on radius here. All right, so great. We come up with a mathematically satisfying result. Physically it seems to make sense. The units line up, the relationships between the parameters line up. Oh, that's great. But who cares? Right? Who cares about rotating disk viscometers? And in particular, why do bioengineers care? Well, some colleagues of mine in graduate school were developing synthetic synovial fluid, right? So the fluid that goes in between the cartilage in your joints. And one important parameter for synovial fluids is the viscosity of the fluid, right? So you basically want it to be viscous enough such that it doesn't leak out of the joints, but not so viscous that it resists the motion too much. So you need tools to characterize that synovial fluid. So they did tests, not with this exact device, but with very similar devices to characterize viscosity. And you can imagine a rotating disk is a heck of a lot simpler than trying to get some plate to scoot back and forth and all that stuff. Another thing is you can use viscosimeters to actually perturb and measure proteins. So if you have suspensions of proteins and you apply a lot of shear stress by spinning them around, you can cause those proteins to actually deform and stretch out. And you can use X-ray crystallography and other techniques to then essentially measure sort of stress and force relationships for proteins. And that's actually very important because a lot of protein changes in their shape and structure result in increases or decreases in enzymatic activity that are fundamental to the signaling of those proteins. And in fact, a colleague of mine studies protein crystallography to actually consider how chemically Alzheimer's disease can progress. The formation of plaques, and you've heard of tau and amyloid proteins. The way those proteins, the shear stress interacts with those proteins in a way that can alter the progression of the disease. So, this matters a lot. Bioengineers need tools like this to characterize viscosities or to apply shear stresses to materials, to cells, to proteins, to biofluids in order to characterize them. So hopefully you care about fluids and about viscosimeters. as much as I do. So, thanks for listening, and good luck with your biofluid studies. Thanks.